At this point, I want to take a break from our regularly scheduled program, and I want to talk about Pythagorean triples, which seems to be some topic out of left field, at least in the context of a complex analysis course. But I want to just explain one cool application of complex analysis, and one place where actually, even though you can talk about Pythagorean triples and there's no complex analysis involved, you can still use the methods of complex analysis to solve these real problems. So what I want to do is let me just remind you that, of course, everyone's favorite result in high school geometry is the Pythagorean theorem, that if you have a right-sided triangle, you know that a squared plus b squared equals c squared. And then Pythagorean triples are solutions. So Pythagorean triple is a solution, A, B, C, where A, B, and C are positive integers. Okay, this rules out the silly examples like 0 squared plus 10 squared equals 10 squared. So that technically is a Pythagorean triple, and that will actually enter into our discussion here. But really, when people talk about Pythagorean triples, they mean non-trivial Pythagorean triples where one of the terms is positive. In fact, they might also refer to what are called primitive Pythagorean triples, which are ones where there's no common factor. Because, of course, if you have the Pythagorean triple, say 3, 4, 5, that's a primitive Pythagorean triple because 3, 4, and 5 don't have any factors in common. Okay, they are what are called relatively prime. There's no factors that you can pull out of 3, 4, 5 to make it any simpler. On the other hand, if you were to say double or triple or quadruple each of those values, let's just say double for now, it turns out that you would get another Pythagorean triple. But in a certain sense, this doesn't feel new, right? This doesn't feel like a new Pythagorean triple because really we just took the previous one and we scale it up by 2, which is basically just saying, you can extend the side lengths of the triangle all by a factor of 2, and then you get another Pythagorean triple. And of course, there's infinitely many of those. Interestingly enough, though, there's infinitely many primitive Pythagorean triples. And I think that this is a fact that we kind of just assume that, of course, there's infinitely many Pythagorean triples. Why wouldn't there be? But it's interesting to note that if you were to change this exponent from a 2 to any larger integer, there's no solutions at all. So if you were to look at, say, a cubed plus b cubed equals c cubed, or in general, a to the n plus b to the n equals c to the n, there are no non-trivial solutions when that exponent is 3 or larger. And this is called Fermat's last theorem. So the fact that there's infinitely many when the exponent is a 2 is interesting. Okay, or at least it tells us a little bit something there. And so what I want to do is I want to recast this in a slightly different scenario. And rather than thinking about the solution a squared plus b squared equals c squared, I'm going to look at the equivalent a squared plus b squared equals c. So in other words, if we want to find a Pythagorean triple, what we need to do is we need to find integers a and b so that the square root of a squared plus b squared equals c. And of course, we know that a and b are integers, so a squared plus b squared will be an integer. So we know that this thing under the square root is an integer. So in other words, this term is going to be the square root of some integer. The question is, when is it an integer itself? So for example, when you have 3 and 4, you have 9 plus 16, which is 25. And so the square root of 25 being 5 tells you that's great. That's a Pythagorean triple. Okay, and so that's the kind of thing that we're going to be looking for. To do this, what we're going to do is I want to keep this equation kind of fresh in our minds here. Okay, so the square root of a squared plus b squared equals c. In fact, let me rewrite that because this is going to be pretty integral to what we do. So a squared plus b squared equals c. So again, we want to find positive integers. So we want to find positive integers a, b, and c, where a squared plus b squared, if we take the square root of that, is c. Okay, so just to write this so that we can see this a little bit nicer. Okay, so that's our goal. And if we think about this quantity here, the square root of a squared plus b squared, is something that we've seen before. It turns out that the square root of a squared plus b squared is the modulus of the complex number a plus bi. Okay, and so we know that that's the modulus of the number. So this actually recasts the problem just slightly into thinking about what are the complex numbers a plus bi, where a and b are positive integers, and where their modulus, in other words, the distance from that complex point and the complex plane to the origin, that distance should be an integer. So you can think about now if we plot the point 3 plus 4i. So we have 3 plus 4i. And then you can compute the distance from that complex number to the origin. And in other words, the value that we call the modulus of the complex number. And it turns out to be 5. Okay, so we have 5. Here was 3. And then this was 4. Okay, so there's our triangle there, with that purple line being the hypotenuse. And of course, this being a right angle I just can't draw. So that's what we're looking for. We want to look for these positive integers. This is a good place for me to introduce the idea of what are called the Gaussian integers. Gauss was possibly the best mathematician that's ever lived. And many things are named after him, one of which is the Gaussian integer. So the Gaussian integers, if you've taken an algebra class, this is a ring, but this is basically just the set of integers of the form a plus ib, where a and b are integers. Remember that the integers, so just recall that the integers are the positive and negative whole numbers and 0. 0 is not positive nor negative. Okay, so these are just the integers a plus ib. In other words, if you were to graph the Gaussian integers, you would end up with 0, 1, 2, and so on, but then I, 1 plus I, 2 plus I, 3 plus I, and so on. And you end up with this grid that mathematicians call a lattice. Okay, so this is sometimes called the integer lattice. And then, of course, it goes in the negative direction as well. And I'm going to stop filling points out right now. So that's z sub I. Okay, and of course, it goes infinitely far in all directions. And so these are the Gaussian integers. But we want to know, what are the Gaussian integers who are a integer distance away from the origin? That's what finding Pythagorean triples is all about. And so here's going to be the cool thing that I want you to think about. Pick some arbitrary complex number. I'm just going to pick this one, but let's in general call it a plus bi. And if you remember, we can compute the modulus, and that's fine. The modulus is, in this case, if this was the number 2 plus I, this wouldn't actually be a Pythagorean triple, but that's okay. But if we look at this, so now let's look at this triangle. Let me color it all in purple. So if we look at the triangle determined by these 3 points, and then we think about the angle of the that one. So if we think about the angle there in the triangle, let's think about what effect does squaring that value have on this complex number. And so if we were to square a plus bi, we have a formula to compute that. But just think about geometrically what happens when we square. We talked about this when we were talking about these functions. It turns out that what you're going to do is you're going to, the argument here, the angle, is going to double. So we'll end up with an angle that's going to be something like, come on, pen, it's going to be like 2 theta, something like that. And then what happens to the modulus is that you square it, and that's the key. So remember that I made this comment at the beginning that seemed kind of out of left field and unimportant, that we're always talking about, if we pick an integer, if we pick a Gaussian integer, we compute the modulus, in other words, the distance from the origin to that point. That modulus is always going to be the square root of some integer. Well, if we square this complex number, since we had the square root of a squared plus b squared as the modulus of this complex number, when we square it, we end up with a squared plus b squared, which of course is an integer. And so that's going to be the key for us. So it turns out that squaring complex numbers is going to give us Pythagorean triples. So we have a plus bi, and when you square it, you end up with a squared minus b squared plus I times 2ab. And it turns out that this is a nice way to think about all of the Pythagorean triples. And this captures, in a certain sense, all of the Pythagorean triples, or all of the multiples of Pythagorean triples. There's some details here I'm gonna slightly gloss over, but this gets most of the Pythagorean triples here. And so just to show you the way that this works, just pick some random complex number. In our case, we already have 2 plus I. Okay, we know that 2, 1, there's no nice number that you can write here to make this a Pythagorean triple. But what happens when you square 2 plus I? Well, what happens is you're going to end up with 2 squared plus I squared plus 2 times 2I. And so what you end up with, I'm sorry, 2 times, 2I. So what you end up with is 4 minus 1, because I squared, of course, is minus 1, and then 3 plus 4I. And then this is a number. In fact, this happens to be the number that we started with. This is definitely going to lead us to a Pythagorean triple, 3, 4, 5. Okay, and so let's just do another one. If you were to pick, say, I should point out that some of these examples are boring, because if you pick something like 2 plus 2I, the argument of that complex number is going to be pi over 4. So when you double it, you're going to get a purely imaginary number, which is going to lead to a not very interesting, it's going to be a degenerate Pythagorean triple. Okay, so it's going to be something like 0 squared plus 4 squared equals 4 squared, which is definitely a Pythagorean triple, just not very interesting. So let's skip over that one, and let's look at 2 plus 3I. And 2 plus 3I is going to lead us to, let's see, 4. What's going to happen here? 4 minus 9 plus 2 times, so 12I. And so this leaves us with minus 5 plus 12I. And so you have a Pythagorean triple, 5, 12, 13. There's another Pythagorean triple. You do have to take, if you're interested in just the positive versions, you have to take absolute values of the real and the imaginary part. And of course, there's some symmetries as well. Because if you go back to the original equation, if you look at a squared plus b squared equals c squared, there's a few things that you can do just to play around with it. Of course, you can interchange a and b. So there's nothing is really gained by interchanging a and b. In our case, you don't get a new Pythagorean triple. Also, you can replace all the values a, b, and c by their negatives, and then when you square, those go away. Okay, so that's essentially what's happening here. So if you want just the positive versions, you can just square everything. And now let's take a number that I haven't thought about before. Let's say 4 plus 5I. And when you square this number, let's see what's going to happen. Let's actually do 5 plus 4I. Doesn't really matter. But so 5 plus 4I, you're going to end up with 25 minus 16 plus 2 times 20I. And so that's going to end up being 9 plus 40I. And then let's just check. This is not a Pythagorean triple that I've ever seen before. Not that I know many of them. But let's just look and let's see what's the square root of 9 squared plus 40 squared. And it happens to be 41. That's amazing. So that's cool. So it turns out 9, 40, 41 is a Pythagorean triple. And so the point here is that even though complex numbers had nothing to do with finding positive integer solutions to some equation, it turns out they can still be really useful. Okay, and so I'll leave it to you to find other complex, I'll leave it to you to square other complex numbers and find more Pythagorean triples. So this is kind of fun, just verifying that that works.